In this video, what we're going to do is look at a titration, acid-base titration. In particular, we're going to look at the titration of a weak base with a strong acid. So weak base, strong acid. So let me bring up a problem here. So calculating the pH of a weak base titrated with a strong acid. So an analytical chemist is titrating 229.1 milliliters of a 0.2200 molar solution of methylamine with a 0.9000 molar solution of HiO3. That's hydroiodic acid. The pKb of methylamine is 3.36. Calculate the pH of the base solution after the chemist has added 60.3 milliliters of the HiO3 solution to it. Note for advanced students, you may assume that the final volume equals the initial volume plus the initial volume of the solution plus the volume of the HiO3 solution added. Round your answer to 2 decimal places. Okay. Calculating pH here. Okay, so here's what we have. We have a volume and a molarity of a weak base, and we have a molarity and a volume of a strong acid. So they're going to react with each other, right? So we'll begin by looking at that reaction of the equation. Typically, I like to put the acid formula first. It doesn't really matter, but I typically put the acid first. So I'm going to put the HiO3. And we're going to react that with methylamine, CH3NH2. Okay. Oops, NH2. Okay, so the acid donates an H+, it goes on to the nitrogen. So you get IO3 minus, and then CH3 NH3 plus, right? So Bronsted-Lowry reaction. These are aqueous all the way around. Okay, there we go. So there's our reaction. There's our equation for the reaction in any case. So now let's do some calculations. Let's do our millimoles of each substance. I guess I'll do the HiO3 first, since I wrote that first. So we have 60.3 milliliters times 0.9 thousand moles per liter, right? Remember, with these titrations, it's useful to have things in millimoles because the volumes are in milliliters. So 60.3 times 0.9 is 54.27. And that's going to be millimoles, right? And then we'll do the methylamine. Okay, now this one is 229.1 milliliters, but it has a lower concentration. So 229.1 times 0.22, and here we get 50.402 millimoles. So let's first identify which one is the limiting reactant and which one's the excess reactant. The limiting reactant is the smaller one, right? So that means that the limiting reactant is the methylamine. And the excess reactant would be the per-iotic, actually we call it per-iotic acid. Iotic acid, I'm sorry, we call it iotic acid. So this is the excess reactant or reagent, okay? So remember, the way that we did this for the previous type of problem was we wrote down the initial number of millimoles of each of the reactants. We're going to do the same thing here. These are 0 initially, right? We subtract the limiting reactant from each of them to figure out how much is left over. And, you know, of course, the limiting reactant, there's not going to be any of it left over. And these are going to go up by 50.402, up by 50.402. Okay, so, you know, that's going to give us some amount there, right? So 54.27 minus 50.402, I get 3.868. And of course, this will be 0, and this will be 50.402. And then this will be 50.402. Okay, now, what do we have here? We have the excess, the base is gone, right? The weak base has been reacted. So we have, you know, we have a strong acid here. There's still some strong acid left over in this reaction. And we have, you know, we have a conjugate base of the strong acid, but it's the conjugate base of a strong acid. So again, back from chapter 16, the conjugate base of a strong acid has a negligible effect on pH. We can ignore it, essentially. And we do have a weak acid here, right? This is a weak acid. This is the conjugate acid of the methylamine. So it does have an effect on the pH, but what we're going to do is we're going to make the following assumption. Strong acids have a much more powerful effect on pH than weak acids do, just like strong bases have a much more powerful effect on pH than weak bases do. So we're going to ignore the contribution of this weak acid. Now, we could go through like a little calculation and show that, in fact, it does increase the amount of hydronium ion, a small amount, but relative to the strong acids, very small. So it's a small difference. And in general, if differences are, you know, 5% is our kind of go-to rule. If it doesn't increase the concentration of hydronium by 5%, then we can ignore it. And that would most likely be the case here. Okay. So we're just going to take a look at this one now. This is a strong acid. So we have 3.868 millimoles of a strong acid left over. And we're going to divide that by our total volume, which is 60.3 milliliters plus 229.1 milliliters. I hope you can see where I'm going with this. If we take the amount of the HiO3 that's left over, the iodic acid, and divide that by the total volume, that will give us the concentration of the iodic acid that's left over after the reaction has taken place. If we have that concentration, we can also say, well, it's a strong acid, so the hydronium concentration will be the same as that strong acid, right? Again, this is all material from chapter 16. So if we take 3.868 and divide that by our two volumes added together, what we get is a concentration of 0.01337. Okay, now why is that moles per liter? Why is it molarity? We've got millis in here, right? But remember, milli over milli cancel. So it's moles per liter. So the millimole really is useful when you're doing these titration calculations. So that's HiO3. Again, it's a strong acid, so the concentration of hydronium is the same as the concentration of the HiO3. Okay, so that means we can calculate pH. A little more than 0.01. 0.01 would give us a pH of 2, so it's going to be a little bit under 2. 1.87. 2 significant digits past the decimal, or 2 decimal place. A little under 2, right? So it is quite possible that the the weak acid that we have here, it might, lower that to 1.86 or even 1.85, but it's a really small difference, and it's something we generally can ignore. It's a lot of effort to calculate that. I mean, we can do it, but for this type of problem, we're not going to. Okay, so keep in mind with that particular problem, what happened was the excess reactant was the HiO3, not the methylamine, not the CH3 and NH2. This problem, our approach actually changes. Our calculations, the details of the calculations change if the methylamine is the limiting reactant, because what will happen is the excess reactant. If the methylamine is the excess reactant, that means we'll have some of it left over, and we'll have a weak base, and then we'll have its conjugate acid. Remember, what do you have when you have a weak acid in a conjugate base, or a weak base in its conjugate acid? You have a buffer, and we use the Henderson-Hasselbalch equation to calculate the pH. So keep in mind that this, finding the excess HiO3 and then that being a strong acid, you calculate the pH from that. That's an artifact of the HiO3 being the excess reactant.